So for today, to start us off, today is kind of a review day, so we're going to be reviewing everything that we've been learning the past 2 days and kind of extending a little bit on it. And so the first thing that I would like everyone to do is, with this graph, I would like you to graph the function -5 times x plus 2 cubed times x minus 1 to the 9th times x squared. So if we are looking at this function here, it kind of looks a little bit, I don't know, that looks kind of intimidating to me. So to get you started, some things that we might need is end behavior. So if we are looking for an end behavior, what kind of aspects will we need to solve for an end behavior? One of them would probably be the degree of our function, and another would be the leading coefficient of our function. And then thinking back to what we did yesterday, some other useful pieces of information might be the zeros of your function, and then the multiplicity that corresponds to these zeros. So I will pause while I let you finish off that problem. So now that we've taken some time, we've looked at this problem, let's look at the degree of our function first. So who can tell me what they believe the degree is? Ryan, have you been able to calculate the degree? All right, who can remind us what the degree is? Okay, and how did you get 14? So the degree is just looking at the exponents. So we have x cubed here, we have x to the 9th here, and we have x squared here. So we wanted to look and see, all right, we have x, and overall, our highest exponent will be cubed 3 plus 9 plus a 2, which will just give us to the 14th power. So our degree is to the 14th power. And I'm going to pause momentarily. All right, so we've gotten the degree now. Now we need the leading coefficient. So if we're looking for the leading coefficient, let's see. Caroline, do you think you can tell us what the leading coefficient is?
Yeah, I got -5.
Yeah, so it's just -5. And so for our leading coefficient, the most important aspect of that is that it is negative. So our leading coefficient here is negative. So if we have a degree that is 14, that means it is even, and we have a leading coefficient that is negative, what will our end behavior look like? Down, down. So both of our arrows will be down. Okay? Now we have to find our zeros. Let's see. Avila, can you give us one of the zeros? So we've got a 0 at -2. All right. Ava, can you give us another one? 1, 0. And Katrina, can you give us the last one? 1? Okay. I mispronounced your name, didn't I? Katie? Okay, Katie. Sorry, different periods, switching it up. Okay, so these are our 3 zeros here. For our 3 zeros, we need to find the multiplicity. Who can remind me what the multiplicity is? So, for example, if we are looking at our 0 at -2, that is this component here. So what is the multiplicity of this factor? Greta, you think you can give it a shot?
3.
3, right? It's just the exponent that is associated with that component. So, because we have a multiplicity at 3, 3 is an odd number. Does that mean that we will pass or bounce off of the 0 at -2? We will pass. All right, we're going to do the same thing for our 0 at 1. If we have a multiplicity of 9, do we pass or bounce? We will pass because that is also an odd number. And then here we have our 0, 0, which has a multiplicity of 2, which means we will bounce. That means that if we have an end behavior that starts down, it's going to go through, pass through that 0. It's going to bounce off of this 0, and it's going to pass through our last 0. Okay. Show of hands, I am confident on this. Show of hands, I would like another example. Okay, let's do one more example. I'm gonna kind of make it up on the spot, so I'm sorry if it's gonna be a little bit trickier than the last one, just a little bit. Okay. So if I say a function that starts with -2, then we have a 3x plus 6 cubed. Then we're going to have a, let's see, how about an x minus 1 to the 10th power. And then we have an, let's make it a little bit trickier, negative x minus 1 to the 5th power. Okay? So I will pause while you take a few moments, and we want to do the same thing and graph this. And I will leave you to it. Great. We've had a little bit of time. What is one piece of information that we need in order to graph this? Quinn, can you give us one piece of information? All right. Our degree is 18. Noreen, can you give us another piece of information? All right. What are our zeros? Give me just one of them. All right. We have a 0 at 2. All right. Shepard, can you give me another 0? -1. All right. And then Oliver, can you give me the last one? 1. Okay. Right. What is Maddie? Ooh, tricky there. Good catch. So this should be a -2. And like I said, I just made this up on the spot, so this is a work in progress for all of us, correct? All right. So now we have our 3 zeros at -2, -1, and 1. Okay? So what is another piece of information that we will need? Ben, could you give us a piece of information? Leading coefficient. So it is 2. You were close. Before, like with this last problem, we said, oh, there's a -5. So our leading coefficient is -5, right? This one, I purposely made tricky for the leading coefficient. Because if we're looking at the leading coefficient, do we just look at the number here? Isn't the leading coefficient the number that comes in front of the largest term, or the term that has our degree in it? Which means that you have to multiply by the coefficient in front of each of the x terms. So if you look at the previous problem, here, what was the coefficient in front of each of our x terms? Just 1. So if you had -5 times 1 times 1 times 1, it's still -5. But here, we have -2 times 3, which is -6, right? Except this 3 is cubed, so it'll be some other large number. But what really matters for us? Does the number matter, or does it whether it's positive or negative matter? It would be the latter, whether it's positive or negative. So here we have a negative number. A -2 is a negative number, times a positive number cubed, which is a positive number, times another positive number to the 10th power, which is still a positive number, times a negative number to the 5th power, which is a negative number. So we have a negative multiplied by 2 positives multiplied by a negative. So is our leading coefficient going to be positive or negative? It's going to be positive. All right. From these two pieces of information, we can get our end behavior. So what will our end behavior look like? Throw in your hands up. So our end behavior is just 2 arrows up. Okay. And what is the last piece of information we need? What do you think, Franny? Last piece of information we need. The multiplicity. All right. So if we look at whatever corresponds with -2, which is this first component here, multiplicity of -2, what is the multiplicity for our value x equals -2? 3. So 3 is an odd number, so it's going to cross. All right, we have x minus 1, so that means our x equals 1 is to the 10th power, which is even, so it's going to bounce at 1. And then over here, for our negative x minus 1 factor, it's to the 5th power, so our multiplicity is 5, which is odd, so it'll cross at -1. Which means if we start up, we cross through this x, we cross through that, and then we bounce off of that last one, we'll get our graph. Okay. Now there's one kind of term that we haven't talked about that you're going to need a lot, and it's going to start showing up a lot later, and it shows up all the time in calculus. Okay? That term is called a limit. If you don't know what a limit is, basically what it means is if you see something that looks like this for your function, this means as you approach a certain number, what will your graph trend look like? So if I said this is the limit as our function goes towards infinity, as it goes all the way to the right-hand side of my graph, and I look at my graph, what's going to happen to my graph as I continue going in the x direction indefinitely? Is my y value ever going to reach a specific number and then stop? Or is it going to shoot off to infinity? So that means the limit as my function goes towards infinity in this direction, the limit is, in the y direction, it's just going to also keep going to infinity. Okay? This is the mathematical way of writing this end behavior here. Okay? So these are equivalent. If I wanted to do the same thing for this component of my end behavior, I'm going to start with the limit again. It's going to be the same function. And then where is it going to end up? Where is it shooting off to? Infinity. But at that point, what x value should I put? So, if I'm thinking about this, I know it's going to shoot off to infinity, but in what direction? Negative direction. So, as it approaches, negative infinity. Okay? This is something that, at this point, I would like you to see it and recognize that when I have this x and an arrow and then an infinity, that means as x goes to infinity. And then here, when I have an x and an arrow and a negative infinity, that means as x is moving in this direction. Okay? All right. Another kind of moving on from this, but also we'll come back to it shortly. If you were to look at your Notability document from the day 1 of this unit, There's a slide on there that has a picture of a cardboard box. I don't know if you happened to like glance at that slide when we were doing it on day 1. But there's a picture that has some kind of cardboard box, and then it has like a kind of like a rectangle on it. If you could get to that page on your Notability document, I will give you a few moments to do so. Day 1 of chapter 6. It is a pink slide. Actually, I think I might have it up. So let's see. It looks like this. Right. So this is a very typical problem that we see once we get into polynomials, because you start working with exponents that are bigger than quadratics, which we use in a lot of applications. So if we look at this box right here, if you've ever had a cardboard box and you have to like put it in the recycling bin, you know how you like take it all apart and you flatten it and you lay it out flat? That's what this is a diagram of. It's just a cardboard box that's been flattened. Okay. And then if you think about the cardboard box with the sides, if you think about it, if you keep this corner once you've laid it flat and then you try and put the walls back up, are your walls going to fit? No, because this will get in the way right here. So what they do for these cardboard cutouts is they just cut off little corners from each side of the cardboard. And then on these black dotted lines here, those are the parts that you fold up to make the sides of your box. Right? And so in this instance here, we said on this side we have a length of 12 inches. On this side we have a length of 10 inches. But we don't know right now how much we want to cut off for each of these small squares. So we're just going to call it some value x. And since we want them to be squares, that means that you have the same length on each of these sides. So they're all x. So that's what it would look like if it was just laid out. But now we want to fold it up. And if we fold it up, you'll have some kind of width, some kind of depth, some kind of height, right? So what would your width be? What would the value of the width of our box be? So we got 10 inches. What would the depth be? Or this length here? 12 inches. And then what would the height be? It would just be x. Do you see that if you took one of these black dotted lines here and you folded it upwards, then this side here would be your height? So that's x. And now let me see if this is the question you're going to ask. I misled you. Because 10 inches and 12 inches aren't actually our side lengths. Exactly. So if you look at this right here, this is the side length we want, because that's the side length that we're going to end up with. Because we cut this part and this part out. These aren't here anymore. So this entire thing might be 10 inches, but then we have to cut off two sides. So this will be 10 minus 2x. And then over here, this will be 12 minus 2x. All right. Now that we have the dimensions of our box, we want to find the volume of our box. And the reason why we want to do that is because we want to figure out what value of x will make it so that we can fit the most we possibly can inside the box. So we can get a maximum volume. Okay? So to do that, we need to find the volume first. How do you find the volume of a rectangle? A rectangular prism. Base times area of the base times height, so it's like length times width times height. Or there they have width times depth times height, whichever way you would like to use it. So our length, I'm just going to say, is going to be 10 minus 2x. Just going in order here. Width is 12 minus 2x. And our height is just x. So if we look at this and we multiply it out, are we going to get a quadratic? How many x's do we have that we're going to multiply by? 3. So we're probably not going to end up with a quadratic. You're probably going to end up with some cubic polynomial. Right? So take a few moments, multiply that out. A warning though, if you are taking this and you are multiplying it out and you distribute like you're supposed to, do you distribute to everything, including that last x? You do not. Please do not. Do not do this part. Distribute these two amongst themselves first, and then after that, then multiply everything that you have by x. Okay? So I'll pause while you take a few moments and multiply that out. I know you might not be done. For the sake of time, I just want to make sure that if you are multiplying this out and you have made a mistake, you don't have to get all the way to the end before you realize you have a mistake. So if we are distributing these first two factors out, I get 120 minus 20x minus 24x plus 4x squared. And all of that will eventually be multiplied by x, which will give me 120x minus 44x squared plus 4x cubed. Great. If I had this and I wanted to know the maximum or the volume of x that I would need to maximize my volume, I wouldn't be able to get it from this equation. So something that might help, let's graph it. If we graph this, we'll definitely need the degree. So what is the degree of this equation? How is this different than the ones that we were just doing earlier? Remember earlier how this was all factored before? It was all factored out. But now this is just kind of in the general form of a polynomial. If it's in the general form here, should we add up all the exponents of the x's, or should we just find the largest one? Just need the largest one. So our degree here would be 3. Because we are in the general form, this is the general form, and it's not factored out. Okay, we have the degree. What is the leading coefficient then? It's just this, which is 4. And then our end behavior. Let's see. Leading coefficient is positive. We have an odd degree. What does our end behavior look like? This one, this one, this one, this one, this one. Okay. Left arrow down, right arrow up. All right. Can we find our zeros from this equation here? We cannot. And because we cannot find our zeros from this, is there another equation that we have already that'll give us our zeros? Oh yeah, up here was factor for us, right? So it's factor for us up here. This will give me 5, and this will give me 6, and that's 0. So I have a 0 at 0. Let's check. 10 minus 2x is equal to 0. Negative 2x is equal to negative 10. Yeah, I think it's positive. All right. So we have one at 5. And we have one at 6. But thank you for double checking me. I was just kind of zooming through it. So, great. Now I have to look at multiplicities. What is the multiplicity for each one of our zeros? They're all 1. So that means that they're all odd. So they all cross. Since our end behavior starts down, that means it crosses through each of our zeros and then ends up. But now we're looking at this graph, and this is just a graph, right? But if we apply it to our problem, right here we have a 0 at 0, we have one at 5, and we have one at 6. If I chose the value 6, and I put it into my original dimensions for my box, what would happen to my box? What if I put a 6 right here? Yeah, so I would get like a -2. Can I have a dimension of -2 on a box? I can't. So you can't have something that's like at 6. If you try 5 with the same dimension here, you'll just get 0, and you can't have a box side length of 0. So you can't have 5. Can you have less than 0? If you have less than 0, what happens to the height? Let's say I have -2. I don't think you can have a negative height. So that means that in actuality, for our problem, because it's a real life problem, you have some kind of domain restrictions on your box. Which means that your domain is in between 0 and 5. Okay, now, because all we have is just this part here, and we said we want to maximize the volume of our box, where do you think you would find the maximum volume on this part of our function? At the maxima, probably be the best bet. Okay? So you'll see a lot of problems like this as we continue on with this. Yes, Eddie? Eventually, we will get to the point where we can find the max point. We are not there right now. If you were asked to do so, you would graph this function on your calculator, and then just use your calculator to find the maximum point. Okay. It is 33. This period ends at 48. Can we do a few long division practice problems? Is that okay? Okay. Because I know long division, we're going to become experts at it, but right now it's like pulling teeth. So let me look up some examples. We're going to start simpler. Let's say under here I put x squared minus 4. Right? Try this problem. I will pause while you're trying it. Right. What we were saying about this problem was, right now, our problem is that we have an x squared term inside our radical. We have a 4, or inside of our division. We have a constant term, but we don't have an x term. And so my suggestion would have been, or would be, add that x term, but add a 0x, which is the same thing as saying no x term. And then keep your constant term in there. And once you have done that, then you can say x times something will give me x squared, which will just be an x. So that means that we'll have an x squared here. Then x times 2 will give me a 2x. And then I have to take the opposite of both. So when I take the opposite of both, I end up with 0 here and negative 2x here. Then from there, I need to take the next term and drag it down. So I'll have a minus 4. And then from here, we say, okay, x times something will give us negative 2x. And that's just negative 2. So then x times negative 2 will give us negative 2x. And 2 times negative 2 will give us negative 4. And once we take the opposite of those, then we end up just with 0. All right, again, we're going to spend a few minutes solving this next problem, and there is something a little bit special about this problem that was different than the other problems. So, students took a little bit of time, and they solved this one out. And so we're just going to finish up this problem because I think it's unique, and I think it will be helpful. For this problem, I'm just going to step through it kind of quickly. But here we have an x. We need to get to a 3x cubed. So x times 3x squared would get us to 3x cubed. And then you have to take 3x squared times 9, which gives you 27x squared. From there, if you take the opposite of both of those, the opposite of both would be their negative equivalents. Then you get 0, and then you get 32 minus 27x squared, which is just positive 5x squared. From there, we drag down this 50x. From the 50x, we know we have an x times something will get us to 5x squared. So x times 5x gets us 5x squared. And then 5x times 9 would give us positive 45x. Yes? Okay, then we take the negative of that, and when we take, or the opposites of those, and when we take the opposites of those, we'll end up with 0, and then we'll end up with 5x. So then we have another term that we have to add down here, so we have 5x plus 30. From 5x plus 30, to get from x to 5x, we have to multiply by 5. Once we have multiplied by 5, we'll get 5x, and then we'll have 9 times 5, which is 45. And we take the opposite of both of those. And once we do that, then we will get 0 minus 15. Uh-oh. We didn't end up with 0. Yes. Yes. So, the process that we're going to use here is the same thing as if you had said, okay, what's 11 divided by 2? Well, I know it's going to be 5 and then something, right? And so typically if you had done long division, it would have been like 5, and then you would have gotten the decimal, and you'd have found out the next digit was a 5. Another way you could write that is, if you have 5, what's your remainder? 1. 1 out of how many? 1 out of the 2 I was dividing by. So another way you could write that is 5, and then the remainder divided by what you were dividing by. So that's what we're going to use here. So here we have this information, which was the factor, and then we're going to say we're left with a negative 15 over, or divided by, what we were dividing by, or over x plus 9. This last part here is called the remainder term, because it is the term that is our remainder. Right. From there, it is 45 right now. So can you quickly get out the homework? You will have 3 homework problems today. Just 3. All right? And so if you look on the Schoology document, let me pull it up really quick. And I know that time's running a little bit short, but bear with me. On this first page, do the first 2. Do not worry about this page. Haven't done it yet. On this page here, just do the first one. After that, stop. Those are the 3 problems that I would like you to do. Okay? Okay, because that is all of the instruction, we're going to pass back tests so you can look at them really quick. And then that is all we'll be doing for today.